So, welcome all of you for the lecture on fabrication of microelectronic devices of the subject advanced manufacturing process. So, see the picture illustration of the regimes of macro, meso, micro, and the nano manufacturing. You can see that micro manufacturing and then meso manufacturing, micro manufacturing, macro manufacturing, and then nano manufacturing were classified according to the size of the products manufactured. You can see the macro manufacturing starts from the product size of less than point that is less than 1 mm, that is 0.5 mm to up to 10 meter, whereas the micro manufacturing starts from microns to nanometer, and then the nano manufacturing starts from the zero point 0.5 micron to the in the terms of angstrom, and then the meso manufacturing lies in between the micro manufacturing and then meso manufacturing. So, what are those examples of the macro manufacturing? So, in simple words, macro manufacturing is the manufacturing of a product which can be seen by naked eye, whereas micro manufacturing cannot be seen by naked eye. So, that is the simplest classification. So, the meso manufacturing lies in between those two. So these are the examples of macro manufacturing. That is, you can see the height of the humans, and then in terms of meter means almost 3.5 meters, and then mouse ant, so the grain of sand. So the human cell, the size of the human cell, will be lies in between the micro manufacturing and macro manufacturing. So that size can be made by means of meso manufacturing, and then there's a virus. The size of the virus, the product, according to the compared to the size of the virus, can be made by means of micro manufacturing. And then the dust particle, so the size of the product which is equivalent to the dust particle size can be made by means of nano manufacturing, and then you can make products, you can make objects with the size of atoms. So that's what the example is given here. And then what are the manufacturing process that we can go for micro manufacturing? You can see the casting, forging, machining, and then chemical blanking. So up to this you can go for that micro manufacturing. And then for micro manufacturing we need to go for ligam, that is lithographic process, and then the carbon nanotubes for nano manufacturing. And then what are the applications where we are using this manufacturing process to make products? So the first one is aircraft, that is lies in macro manufacturing, and then automobiles, machinery, gears, and then ICs even come under macro manufacturing, and then the gear for MEMS, that is micro electromechanical systems, and then the features inside that integrated circuit were made by means of micro manufacturing. So in this lecture, we are going to see about what are the manufacturing process or the machining process used for making micro level or nano level products. You can see here, so in an automobile, what are all the microelectronic and the micro electromechanical devices were present in a typical automobile. You can see that it's called stereo, engine management system, and then the sensors. Most of the sensors were made by a micro machining process only. So the air conditioning, temperature sensor, humidity sensor, light sensor, oxygen sensor, all the sensors which gathers data and then gives to the engine management system were made by micro manufacturing or micro machining process. So this is an IC. You can see that the first picture shows you a 300 mm wafer with a large number of dies fabricated, and this is the this one is the detailed view of an Intel 45 nanometer chip, which is having a 153 bit SRAM, stationary RAM, and then image of an Intel Itanium 2 processor. So this is the processor. And then you can see that outline of the fabrication sequence of an integrated circuit. So how the ICs were made from the raw material. So how the crystals were grown, and then how it is cut down, and then how the crystals were shaped or made into the shape of a small wafer, and then how it is get out, and then how the bondings were made with other elements were shown here. So this is the general fabrication sequence of an IC, that is integrated circuit. And then we are using semiconductors for the making of all the sensors, that is microelectronic devices. we use the semiconductors because the electrical properties of the semiconductors lies between the conductors and the insulators. So they are having the resistivities between 10 to the power of minus 3 to 10 to the power of 8 ohm per centimeter. So because of the electrical properties, we can add or we can what we call we can change the properties of the semiconductors by adding some impurity atoms known as the dopants. So we are using silicon as the semiconductor widely because the factors such as the abundance of the silicon in the earth crust. So oxygen is the most abundant element on earth crust. Next to that, silicon is largely widely available. That's why it is economically attractive also. So instead of germanium, so we are using silicon. Even though the germanium is having a very good properties, we are using a silicon instead of germanium as a semiconductor. So these are the operations how to get the silicon from the raw material, that is silicon ingot, and then how the process, so how to produce the wafers by means of that saw or the diamond bonded wheel, and then how it is made into, you see the wafers here, how to get the wafers, the process available. So the very first process we are going to see about is the film deposition. So the films are used extensively in the microelectronic devices processing in the insulating and conducting types. So those materials are insulating and conducting types. What are the most commonly deposited films? That is polysilicon, silicon nitride, silicon dioxide, tungsten, titanium, and aluminum. So these are the materials widely used. So how the films were deposited? As I told in the very first slide, so we are going for that micro manufacturing. The size of the product will be in the terms of microns. That is, it will not be visible to naked eye. So these films can be deposited by several techniques, including variety of pressures, temperatures, and vacuum systems. By using any one of these two or combining all these, that is vacuum deposition, sputtering, and then chemical vapor deposition. In that we are having three types, that is atmospheric CVD, low pressure CVD, and then plasma enhanced CVD. So what is sputtering? So sputtering is the bombarding a target in a vacuum with high energy ions. So usually we use the arsenic, aluminum, or copper. So as the ions impinge on the target, the atoms are knocked off and are subsequently deposited on wafers mounted within the system. So you will get that uniform coverage. So we are having recent advancements in the sputtering process, that is radio frequency power source RF sputtering, and then magnetic field sputtering, that is magnetron sputtering. So the next one is the chemical vapor deposition. So in this process, the film is deposited. So by the way of reaction or decomposition of the gaseous compounds, while we are using that gas, it will decompose and then it will deposit as a film over the substrate surface. So using this technique, the silicon dioxide is deposited routinely by the oxidation of silane or chlorosilane. So we use these two processes, that is continuous atmospheric pressure CVD or low pressure CVD. You can see this chemical vapor deposition process. So you can see that vapors here. So these are the vapors. The vapors are kept in a conveyor belt, and then we are passing the gas, nitrogen gas, through the chambers. And then what will happen? The nitrogen gas will decompose, and then it will form a layer. It will form a film over this vapors. So the exhaust will come out in this way. So this is one type. Another one type is the low pressure chemical vapor deposition. You can see that in the earlier type we have that atmospheric pressure, whereas here the pressure will be reduced. So we need to go for some pressure reducing mechanism. So we are having it wafers fitted here, and then the pump is there to extract the air. So we will have a three-zone furnace. So similar to that the CVD process, the only thing is we are having a low atmospheric pressure, that is less than 1 atmospheric pressure. Now the next process of making that wafers is by oxidation. So what is oxidation? It is a term refers to the growth of an oxide layer as a result of the reaction of oxygen with the substrate material. So the normal oxidation process is used here to make a film over the substrate. So the thermally grown oxides display a higher level of purity than deposited oxides because they are grown directly from the high quality substrate. So instead of depositing oxides, we need to go for growing the oxides on the surface of the substrate. That is by means of thermal mechanism. So what we are using is the silicon dioxide. As I told already, silicon is most widely abundant material. So we are going for the silicon dioxide. So the most widely oxide used is silicon dioxide nowadays, and then it is having very good characteristics, and then it is a gate oxide material also. So the silicon surface is having extremely high affinity for oxygen, so that you can get very easily the silicon dioxide. And then the freshly sawed slice of silicon will quickly grow a native oxide of 30 to 40 Armstrong thick. You can grow a oxide layer of thickness 30 to 40 Armstrong thick. So there are two types of oxidation. One is dry oxidation and then oxidation. So what is a dry oxidation? As the name implies, the dry oxidation is carried out at some temperature. That is the range of temperature is 750 to 1100 degrees Celsius in an oxygen-rich environment. So what will happen? Ultimately, an oxide layer will form, and then this oxide layer will grow from the silicon surface outward. That is from inner surface to the outer surface. That is dry oxidation. So you can see that the diagram here. So how the dry oxidation carried out. This is the silicon substrate, and then the silicon dioxide surface. So actually, this is the original SI interface. That is the silicon interface. Over that, we are having that silicon oxide. This is the silicon dioxide. So then the wet oxidation, as the name implies, we are having a water vapor as the atmosphere. So what will happen? The water present in the water vapor will be affecting that oxidation process. So the growth rate of oxidation is more because during the wet condition, because of the water present, the oxide will form more, and then the oxide density will be very less. Whereas the growth rate is more, the oxide density will be very less. So what we commonly use is both dry and wet oxidation methods. So first we will use dry and then wet and then dry oxidation method. So that is a three-part layer. And then the next technique of making that wafer is lithography. So what is lithography? It is a process by which the geometric patterns that define devices are transferred to the substrate surface. So we need a geometric pattern over the substrate. So how the electrical connections or how the devices has to work. So that is made by a process called lithography. So what are these lithography types? You can see the types of lithography, that is photolithography, pitch splitting, immersion lithography, extreme ultraviolet lithography, X-ray lithography, electron beam and ion beam lithography, and then soft lithography. So you will see that one by one. So these are the general characteristic of lithography techniques. So what is the wavelength used, and then what is the size of the film? That is, you can see that 350 nanometer. So this is photolithography. You can see that from the diagram. The photons were made to fall on a substrate. You can see that photons were made to fall on a substrate, and in the presence of air, and then you can have that resist over it, and then a contact mask over it. So you can get that beam density, that is of zero point 0.5 in microns. So that will create the resist there. That is the film over there. You can see that wafer, how the wafer is produced. You can see that the first figure. So a check will be there over the substrate, that the photoresist and the thing with a layer. So that is made to fall over it, and then it will be spinning to get the final shape. You see here. So when the evaporant or the solvent is evaporated, we will get the final shape of the film. And the next one is the wafer steeper technique, and then wafer step and scan technique for making the wafers. And then the how the pattern were transferred by the photolithography. You can see that how the patterns were transferred, because this is the oxide layer, and then over that layer we are having a photoresist. So you are passing the UV radiation or laser over it to that photoresist. So what will happen? So the you see here. So the developed image. So what pattern we need, that is made here. The developed image is made here, and then the remaining portions were etched. That is the remaining portion of the silicon dioxide were etched, and then the photoresist is removed. The top portion is called the photoresist. That is nothing but a pattern. So how what area has to be machined, that area only machined there. That is called as the photoresist. So if the photoresist is removed, the shape of the photoresist we are getting we got on the wafer. That is the silicon dioxide layer that flip. So the next process is pitch splitting. So it uses the conventional lithography in multiple stages. So the thing is that it involves breaking up the desired pattern into two complementary portions and then creating corresponding mask. So that is called as pitch splitting. So there are two forms. One is double exposure, another one is the double patterning. These are the two forms of pitch splitting. You can see that double exposure. So the same principle here. So you see that is the substrate and then the target layer. Over that we are having a resist, photoresist, and then the mask and the reticle. So how to develop the photoresist and then second mask and then develop the second exposure and then develop the photoresist, etch the target layer. So etching means the remaining layers has to be removed. Then finally we will get the shape of the resist in that wafer. You see here, so this is the target layer before etching. So the final layer after etching, you can see here. That is the double exposure, and this one the next type. And then the immersion lithography, as the name indicates, it is inserting a fluid with a very high refractive index between the final lens and the wafer. So mostly we use water as a fluid. It requires a careful process controls, especially the thermal controls. And then is the X-ray lithography. So it is very superior to the photolithography because of the wavelength is very short, and then the large depth of focus, and then it is very expensive. So only the research laboratories will have the setup of X-ray lithography. You can see the diagram of that X-ray lithography illustration. The X-rays were passed and then the photoresist were kept here. So the X-rays will remove that area and then we will get the image. We will get the area where the wafer has to be machined. Next one is electron beam and then ion beam lithography. Instead of photons, instead of X-rays, we are using the electron beam and then for ion beam. So in electron beam and ion beam lithography is superior to photolithography in terms of attainable resolutions. So you will get a very good resolution, and then it involves very high current density in a narrow electron or ion beam, which is known as the pencil sources. Yeah, as we know, so the electron beam and ion beam will come in very narrow, very narrow. So that's why it's called as a pencil source. So the resolutions are limited. That is about 10 nanometer because of the electron scatter. And then the main drawback is that it has to be maintained in a vacuum. So as we know, so electron beam and the ion beam should be maintained in a vacuum. So it involves equipment complexity, and then the production time will be increased. So and then the scan time for the wafer is also more than the other lithography process. So this is the electron lithography. You can see the diagram. When electrons were made to fall on the resist, the negative electrons will emit from the surface. So it is carried out in vacuum. So this one is ion beam lithography. You can see the same thing. The substrate resistive, you are passing the ions. It is carried out in a vacuum. So you can see the width of the ion beam lithography. The line which is 0.1 microns. And the next one is a soft lithography. This is the processes for pattern transfer. So how the patterns were transferred, and then we are using a master mold, and then elastomer has been used commonly. We use the polydimethyl siloxane, that is PDMS. We use that one for that soft lithography. You can see that PDMS mold for soft lithography. You can see the silicon substrate. So over that we have developed a photoresist, and then we formed the PDMS over there. PDMS stamp is cast over the photoresist, and then finally the PDMS stamp is peeled off. Peeled off, we will get the where the stamp is there. This is called as the cured PDMS stamp. Similar to the rubber stamp, this is called as the cured PDMS stamp. So these are the soft lithography process, that is a micro transfer molding, that is MUTM. So this one is another one is micro molding in capillaries, that is called as mimic micro molding in capillaries. These are the two soft lithography process. You can see that the process of micro transfer molding and the micro molding in cavities, that is mimic. So the PDMS stamp is created, that is prepared, and then fill the cavities with the polymer precursor. And then the press stamp against the surface allow the precursor to cure, and then peel off the stamp. If the stamp is peel out, you will get the layer. That's all. So the same thing for here also. Prepare the PDMS stamp and then drop it, press it over the substrate, remove the excess liquid, that is polymer, and then peel off the stamp will make the material, make the process. So this and all in microns, that is the size will be in microns. And then how the films were removed. As I told already, the substrate over the substrate we are having that the films. The entire area of the film is not used. We use only the selective area. So the remaining area which were not used should be removed. That removal process is called as etching. So the etching is the process by which the entire films or particular sections of the films are removed mostly. So we have to select the material without etching another. So the material should etch only the film. So in silicon technology, and the etching process must etch the silicon dioxide layer effectively with minimal removal of the either the under the silicon or the resist material. That is the over the silicon substrate. That film should be removed, not the silicon or the any other resist material. Like that, you have to select the etching material. So it involves two steps. One is wet etching, that immersing the vapors in the liquid solution, usually acidic. So because of the acidic nature, the layer will be etched very easily. So the primary feature is they are isotropic, that is they etch in all directions. If you immerse the the vapors in acidic solution, it will be removing the layers, removing the materials in all directions at the same rate. So what are the isotropic agents, and then why the agents were widely used? Why it is used? Because of these properties, and then you can see that various etching methods, that is etchants used in a dry etching process and then wet etching process. What are the target materials, and then etch rate, the target material, and then etch rate for different materials. You can see this diagram. So this one is the isotropic etching. You can see here. So the etch material is the silicon. So etch material is silicon. We are having the mask. This is the mask layer. If you immerse in that etchant, then it will be removed under the layer. That is called as the undercut. Under the layer also it will remove. Next one is anisotropic etching. So this is when etching is strongly dependent on the compositional or structural variation of the material. We will go for that anisotropic etching. There are two types. One is orientation dependent etching and vertical etching. We can see that the orientation dependent etching (ODE), how it is carried out, and then vertical etching. So very simple process. The next one is dry etching. So the integrated circuits are now etched exclusively by dry etching, which involves the use of chemical reactants in a low pressure system. So also the dry etching process requires only small amounts of reactant gases, whereas the solution used wet etching have to be repressed periodically. So that is the one thing we need to carry out. So the dry etching usually involves a plasma or discharge in areas of high electric and magnetic fields. Any gases that are present are dissociated to form ions, photons, electrons, or highly reactive molecules. So you can see that the table which I shown you earlier. So how the silicon etching is carried out in wet etching process and then dry etching process. In the presence of the etchant, you can see that etchant potassium hydroxide ethylene diamine, and then here you can see that surface 6, and then temperature, what is the etch rate in micrometers per minute, and then what are the dry etching techniques. We use the sputter etching, reactive plasma etching, physical chemical etching, and then cryogenic dry etching. So these are the different process. You can see that this is sputtering, and then by means of ions, and then then chemical etching, and then ion exchanged energetic etching, and then ion enhanced the inhibitor etching. These are the types of etching. And then how the reactive plasma etching is carried out. You see here, this is the film surface, and the generation of etchant species, and then diffusion to the surface, and then absorption carried out. So this the etchant species will react with the film here. Then what will happen? Due to the reaction, the film atoms were desorbed. That is, it is removed from the layer, and removed from the film. You can see here, it is removed from the film and then diffused into bulk gas. It is carried out as a bulk gas. So the HN species from the HN we are creating the HN species, so that will diffuse to the surface, and then it will attach to the atoms of the film, that is called as absorption, and then it will react with the atoms, and then it will remove the atoms from the film surface, that is called as desorption, and then those removed atoms were diffused into a bulk gas, that is the reactive plasma etching. And this one is the example of that showing that deep reactive ion etched trench. You can see here. You can see this one very small in nature, very minute in nature. How it is carried out, you can see here also. Near vertical side walls produce the deep reactive etching and ionotropic etching bars. These are the cavities created. You can see here. These are the cavities created. Very minute, and the microns range. The cavities were created. And then here also you can see that example of the cryogenic dry etching. You can see that 145 micrometer diameter. This one is 145 micrometer diameter, etched into the silicon using the 2 micron thick oxide. Surface temperature was minus 140 degrees Celsius during etching. You can see that how the areas were removed to form a gear. And then wire bonding and packaging. This is the next step. That is the making of the ICs. After the ICs were made, after the wafers were made, and then oxide layers were created to get the required the device shape. It should be bonded to the wires, so to carry out the to carry the current, electric current. So once the chip has been attached to the substrate, it must be connected electrically to the package leads. Then only the integrated circuit or the any sensor will work. So for that we need that bonding of the chip to the electrical connections. This is accomplished by wire bonding, very thin wires. That is, you can see 25 micron diameter or 0.001 micro inches. So the wires are made up of gold, that is gold wires from the package leads to the bonding pads located around the perimeter or down center of the die. So we use the gold wires for the transmission of the electric current. You can see that same photograph, a scanning electron micrograph photograph of the wire bonds. You can see these are the gold wires. The gold wires are connected to the wafers. So this was the detailed view. You can see this one is the detailed view of the gold wire, which is connected to carry out the to conduct the electricity. So this is the very detailed view, and then very magnified to 600x. You can see that magnified to 600x of that gold lead. You can see these are the etchants, that is etched parts created on the surface. So, and then wire bonding, the bonding pads are on the die are typically drawn at 75 to 100 microns per side. So they were attached by means of thermocompression or ultrasonic or thermosonic techniques. How the bonds were attached to the wafers or the IC substrates. You can see here, these are the illustration of thermosonic welding of gold wires. So these are the gold wire, how the gold wire is joined to this die. So how it is formed? That is, an arcing forms the gold ball. A gold arc is generated, and then gold ball is generated here. And the ball bonds with the die, and then the position tip over to the package lead. Then it is tip over. That means it is inverted, and then stitch bond on lead, and then break the wire. So this is the process. You can see here. Then we have to break out this one. So this is the die and then the wire in the form of loop. And then packaging. So now the connected circuit. So now the integrated circuit is connected to the wires, to the surface or the wafer, and then now it is ready for the packaging. So that is called as the final packaging. The circuits are mass produced on the wafer, but are then packaged individually. So ICs are used for military and industrial applications, require packages of particularly high strength, toughness and resistant to temperature. So depending upon the usage of the IC, so the packaging technique or packaging parameters will vary. So we are producing packages from polymers, metals or ceramics. So metal containers are made from cover, an alloy made up of iron, cobalt and nickel. And then ceramic packages usually use aluminum oxide or alumina. And then plastic packages we use mostly the polymers. They are inexpensive and are high lead counts, but they cannot withstand high temperature. And they are not hermite. Hermite means they will not fully cover the whole area. So these are the packaging styles, that is dual inline package, flat ceramic package, surface mount package, ball grid package, chip on board, split chip on board, and then system in package design. You see one by one. This is the dual inline package. It is very low in cost and very ease of handling. They use thermoplastics, epoxy ceramics. This is the dual inline package. You can see here. So these are the bond wires, the molding compound, lead frames. So all these things were in miniature size. All these things were in miniature size. The next one is flat ceramic package. The name indicates that the package and all of the leads are in the same plane. So that is called as it is a flat ceramic package. You can see here the ceramic cover, the circuit die, and then these are the bonding wires, and then the glass seal. You see the number of wires. Ceramic package. So this is the flat ceramic package. And then surface mount package, it is soldered onto a specially fabricated pad or land. So the package size and layouts are selected from standard patterns. So that is the surface mount package. You can see that various composition, that is various forms of the surface mount package. You see how the this is through hole surface mount package, butt joint, and then crow's foot. You can see here. This is crow's foot, and then the gull wing, how the surfaces are mounting. And the next one is ball grid arrays. This is the way of achieving tight packing of connections to avoid a difficulty of cylinder connections. That is by means of ball grid array (BGA). So the spacing between the balls can be around 50 microns. You can see here. This is the ball grid array. This is the PCB, BT epoxy PCB. This one is the IC. We are having the wire bond, die pad, solder, signal, ground. This is solder mask. This is the ball grid array. Next one is the chip on board. The chip on board design (COB) refers to the direct placement of chips on the other layer on the circuit board. Directly we can place the chips on the circuit board. That is called as the chip on board. Then the electrical connections are made, and then after wire bonding, the final encapsulation, final covering with the epoxy is necessary. That is the chip on board. And the another one is flip chip on board, that is FOB. So it involves the direct placement of a chip with the solder bumps onto a array of pads on the circuit board. We are directly placing the chip on the circuit board. So what is the main advantage to flip chips? This one is and the ball grid array is that the space around the package normally reserved for bond pans is saved. That a higher level of miniaturization can be achieved. So you can go for a very small sizes. That is the advantage of FOB and COB. You can see here. So solder plated metal balls and pads on the printed circuit board. You can see this is IC, this is the PCB, and then flux application and placement. You are applying the flux and then placing the IC over the PCB, and then reflow the soldering. The solder is reflowed. And finally, because of the melting of the solder, so the IC is fixed over the PCB. That is called as the encapsulation, fully covered. Next one is the system in packaging. It engrafts more than one IC into a package. So these packages can be integrated horizontally or vertically. It is very complex and requires high power density. You can see here horizontal placement of the system in package, that is a flip chip type. Next one is the interposer type stacked structure, how the chips were carried out, chips were attached. And then this is interposerless stacked structure with throw silicon. This is another type. And then you can see embedded structure. You can see here WLP, that is the wafer level package. So now finally we are coming for the PCB. So what is the PCB? A PCB is a substrate for the final interconnections among all of the completed chips. So far we saw about the manufacturing or making of the chips, that is ICs, integrated circuits, very small miniature level or micron level chips. How the completed chips are connected and serves as the communication link between the outside world and the microelectronic circuitry within the each packaged IC, that is called as the PCB, printed circuit board. So usually they contain the discrete circuit components like resistors, capacitors, inductors, high performance transistors and crystals. All these things were made into a single board, that is called as the printed circuit board. You can see the diagram, so the photograph. So this is the PCB, actual PCB. So this area I will having the DIP package, solder, lead, hole, and in this area I will having the partially buried hole, gulving, as I told already, gulving, and then buried EF hole. You can see insulation layers, surface signal tracks. These are the tracks available, and the surface mount land, internal processors. Those were present in the IC, that's PCB. So what is a P? It is basically a plastic material. The base of the PCB is nothing but a plastic resin. It contains several layers of copper foil so that it will conduct the electricity. So single-sided PCBs have copper tracks on only one side for an insulated substrate, whereas the double-sided boards will have the copper tracks on both sides. So multi-layer boards will have the alternating layers of copper and insulators. So the insulator has to stop the flowing of current, and then copper will conduct the current to the circuits. So these are the design considerations given for that PCB. So we use only wave soldering because on one side of the board, and then should be laid out carefully on the PCB. So because of the good solder, by the solder only we are attaching the chips to the PCB, that is substrate. The spacing of IC is determined by the mainly by the need to remove heat during the operation, because if you keep the devices close enough, then the heat evolved during the operation will be more. So that's why we are keeping some space. There should be sufficient space for each package for the reworking and then repairing without disturbing the adjacent layers, that is adjacent devices. These are the design considerations. You can see this one. So, so this is nothing but a gyroscope sensor used for automotive applications. So in that gyroscope sensor, you have this sensor here. Actually, this sensor is nothing but here. This is shown here. You can see that all the areas where the current is carried out, the devices are kept. So how these devices were made? That is the fabrication of micro electromechanical devices and systems. So far we discussed only about that ICs, that is electronic devices or integrated circuits. So how the micro electronic and then mechanical devices and systems were made. So there are four categories, that is micro electronic devices, micro mechanical devices, and then micro electromechanical devices, and then micro electromechanical systems. The last one is called as the MEMS, micro electromechanical systems. So just we need to know about the only the definition of the microelectronic devices. The microelectronic devices are semiconductor-based devices that often have the common characteristics associated with the extreme miniaturization and use electrical principles in that design. So they use only the very small components, very small, that is miniature in size. That is microelectronic devices. The next one is micro electromechanical devices. So these are the products combine mechanical and electrical or electronic elements at very small in scale, very small, very small. So all sensors, most of the sensors were the example of the micro electromechanic devices. You just recall the photograph I shown you in the second slide of an automobile, which shows all the sensors. All those things were micro electromechanical devices. And then micro mechanical devices. So these are the products that are purely mechanical in nature and have dimensions between atomic length scales and few millimeters. That is in Armstrongs. So the examples were very small gears and hinges. Those were micro mechanical devices. And then micro electromechanical systems. So these are the micro electromechanical devices that also incorporate an integrated electrical system in one product. If you have only one device, then it is micro mechanical device. If you have an electrical system also integrated into it, then it is called as micro electromechanical systems. So they are very rare. They cannot be compared with micro electronic or micro mechanical or micro electromechanical devices. So the digital micrometer devices and then air bag sensors. The examples of that micro electromechanical system, the MEMS, were that airbag sensors in automobiles. And then how these devices are machined, that is micro electromechanical systems, micro electronic devices, micro mechanical devices, micro electromechanical devices. So how these devices or systems were manufactured, the process known as the micro machining. So, what is micro machining? The production of features from micrometers to millimeters is called as a micro machining. As I shown you in the very first diagram. So, micro machining is the machining of making the products in terms of millimeters. So, normally it is not visible to the naked eye. So, there are two types. One is the bulk micro machining and then surface micro machining. So this one is the bulk micro machining. You can see that steps. The diffuse of dopant in the desired pattern. The substrate we are using N-type silicon, and then diffused layer is the P-type silicon. And then we have, over that we deposit a masking film. That is deposit and pattern masking film, a non-etching mask. That is silicon nitride. So it will not be removed. And then orientation dependent etching relieves behind the structure. You can see that. So that will not be removed, the remaining areas are removed. So that is called as bulk micro machining. And next one is surface micro machining. You can see here you do a deposition of photosilicate glass, that is PSG space layer, and then lithography. By lithography we are etched the layers and then deposit the polysilicon over that layer, that is step 3. And then again you are by means of lithography you are etching the polysilicon, and then the selective etching of the wet etching of PSC leaving the silicon substrate. So only the suspended cantilever is there. So that is used for any other component. That is the surface micro machining. You can see this one. This is a micro lamp. This is a micro lamp produced from a combination of bulk and surface micro machining process. You can see here. This is the cavity of a zero point 0.1 micrometer cross. This is the film. The film is etched for 2 microns thickness. 2 micron thickness film etched by means of the bulk machining, that is bulk micro machining and then surface micro machining process. So far we discussed about the fabrication of ICs and then micro electromechanical devices. So what are the processes used for fabrication of those ICs, how it is carried out, that is lithography, and then etching, and then wire bonding, and then packaging, and finally that micro machining process. So, so that's all about our lecture. Thank you so much.